Okay, hope you can see the slide. Is it visible, right?
Yes, ma'am.
Okay. So till now, whatever we did, it is like a huge portion where PV installation will carry out. So now we have to think about the derating factors which are affecting the power output of a system. And we discussed that temperature is one of the main phenomena which is going to affect your PV output, because if your cells are too hot because of heat loss, your output will be reduces. So similarly in the colder region, means if the temperature is less, of course it looks the output is too good, but other parameters like dirt accumulation or salt accumulation and of course snow accumulation will going to create other problems like corrosion. So in that way, we'll find out which are all the factors are affecting the system. So first one, losses in utility interactive PV system, because we know that PV systems can be connected for grid system. Similarly, we can use it only for your domestic purposes, because this thought of installing a solar cells or solar plant, solar panels was developed for rural areas before. Rural areas where we cannot communicate, where you cannot drag your transmission line for a longer distance. In those areas we have planned. But when you think about a huge generation, see now we have so many power plants. So in that power plants, you can't generate and you can use it for your loads, right? You have to give it to the grid system, and from the grid you are going to demand how much you needed for your load operation. So in that case, they're saying the losses in utility. The losses, the term says without matching your input to the grid system as well as output of an inverter, if the both doesn't match, then you cannot interact. That is the first point. So we always think about synchronizing the system by considering what is the voltage, what is the current, what frequency we are transferring. Is it of a single phase system, three phase system? All these things we have to be considered. Okay. So in that cases, see, there are a vast number of factors that prevent PV system from working at maximum efficiency. Of course, when you consider a solar system, first of all, we are getting a efficiency of just 35%. Remaining 65% is like from the energy converting to the form of production, we lose so many things. So 65% of energy will be lost. Only 35, we want to get that 35 completely. But still in that also, there are so many losses will exist where they'll reduce the maximum efficiency and reaching their rated output. Okay. So these factors are accounted for those a process called derating, means which are affecting the output, which are reducing the maximum efficient output of a PV cell. So that factors we call it as a derating factors. I hope already I have shown the calculation where we are multiplying the cofactors, that is the derating factors with respect to temperature, with respect to shading, with respect to dirting. So we have an individual parameter and we are all multiplying those and finding what exactly the losses are happening and how it is affecting the maximum output. So that's what say calculation of derating factor for the major sources of losses. Loss is outlined here and we are going to demonstrate. Considering these derating factors, we are going to demonstrate one example where it shows how your yield will be varied, how your yield will be affected in terms of calculation. Fine. So first parameter, as I said, temperature. So any of the system, if you consider the derating factor in PV panel, first of all, we consider your temperature. So temperature is a huge effect on your power output. Power output in the sense, if your cells are too hot, if cells are too cold, so then we can find the difference of power losses. So that's what they say. The temperature at which the PV module operates has a large effect on its power output, and high operating temperature. High operating means hot temperature. So because your cell will be manufactured with the range, definitely minimum and maximum. But if it concentratedly, if you are getting high temperature, I hope you have heard the term called hotspot. Hotspot, if it happens, it will going to damage the system. So similarly, here just talking about the temperature, let us assume high temperature, high operating temperature will going to create a power loss. Power loss in terms of I square R. That is a common loss we used to represent. Okay. And the effect of temperature on output varies from module to module because we know that the cell manufacturing, there is a small variation. If you assume that, okay, I'm getting all the 10 modules from the same company, but still there is a small variation. Maybe your in panel capacity can be varied or panel size can be varied so that you cannot say, okay, for one module, what is the output? The same can be expected in second because when you install a PV modules on the roof system, see some area may be a little bit shaded, some area is completely getting a irradiation. In that case, your output will be varied. So that's what they say. The effect of the temperature on output will varies from module to module. And definitely we have to calculate based on the temperature coefficient. So in the last class, when we discussed about the maximum and minimum voltage calculation, we got a chart where it represents a temperature coefficient with respect to power, temperature, and power, voltage, and current. So using the temperature coefficient, we have to check it out. Each model, what is the output? And that's what they say. The module to module, your value will be varies. You cannot say it is a constant value. I can use it directly. So in order to make a more realistic estimation of a system, so we need to calculate what is the derating factor. And that derating factor means it is just like multiplying with a voltage drop as we consider 1%. Similarly, for the safety purpose, we have multiplied with 1.1%. So similar way, we are going to finalize, means each country has its own terms and rules and regulation, where for temperature, okay, they'll specify, okay, this is the value. Whenever you multiply, let us assume you are getting 27 degrees Celsius, and that should be multiplied with the temperature coefficient. That is fine. Then derating factor, that also to be added, considering that you have to take what exactly the output. So that is the first parameter, temperature of the PV module. So here is an example. I think we already discussed this. We had a two category because we need to showcase how really your temperature is affecting the system and how the resultant temperature efficiency we are getting it. So here two examples has been given. So one is, you can see Sydney, Australia, they have taken example where the derating factor for the sharp modules installed in Sydney, that average ambient temperature is 23 degrees Celsius. Okay, so how they are going to do the calculation, you can just assume. So here you are getting 23 degrees Celsius as a average ambient temperature. That is nothing but 73.4 degree is the actual temperature is existing at that place. And this is your ambient temperature. As per the calculation, if you find out the difference between your cell temperature and ambient temperature, you guys are going to get 23 degree Celsius. So let's see what is the first one. From the ambient temperature, the cell temperature is calculated. Okay, so what is that? They are given it as 23 degree of our cell temperature, and our standard condition, it is 25 degrees Celsius. So if you do the summation of this, you're going to get 48 degree. Throughout, you're getting 48 degree. But whenever we want to do the calculation, we are determining what is the actual difference, how much temperature is varied between or varied from your standard ambient temperature, because we know 25 is the standard, and out of that, what exactly the difference we are finding it. So how you have to calculate the difference between the cell temperature and your standard testing condition. Standard testing condition is how much? 25 degree. And you guys has calculated by additioning the ambient temperature and standard temperature, you got 48. Do the subtraction. Hope again we are getting the same answer, that is 23 degrees Celsius. Means this is actually giving the difference between your cell temperature and standard condition. Then the table means electrical data, when they're providing the product or a model to you guys, they will be specified with the coefficients. Already as I explained, voltage, what is the voltage coefficient, what is the current coefficient, was it the maximum power coefficient, will be given in the chart. So from there, we have a value called 0.485%. But when you want to get it in terms of a volt, so it should be converted to decimal. So I have converted this as 0.00485. So this is the value already available in the electrical data sheet. We are taking it directly and I'm converting into the decimal format. So you're getting 0.00485. So this is the temperature coefficient. So as per the theory we discussed, so the temperature means difference of a temperature should be multiplied with temperature coefficient. So you got 23 degree and multiplied with 0.00485. So it is going to contribute to some numerical term that is 0.11155. So this value is very, very important because it will going to represent what exactly the resultant temperature efficiency. Okay, so you can see here to calculate the temperature, this figure must be subtracted from 1. Means we are considering generalized, we are considering 1 as a standard category that should be subtracted from whatever the value we got it as multiplication of your temperature coefficient and a value of 23 degree Celsius. So we guys are getting an answer called 0.88845. So this represent what is the actual temperature efficiency or resultant temperature efficiency of that cell. So you can conclude that therefore the resultant temperature efficiency is 88.8%. So this is for the temperature of 23 degrees Celsius. Okay. Or else you can consider in a Fahrenheit that is 73.4 degree Fahrenheit. But normally we go for 23 degrees Celsius because our ambient temperature is considering 25 degree Celsius parameter. Okay, this is one of the category where you have assumed the temperature is bit high. So let us take one more derating factor. Example of Berlin. So here the temperature has been reduced. So you can see here your temperature is 49.64 Fahrenheit, or else you can consider it as ambient temperature as 9.8 degree Celsius. So we'll go with the same procedure. Okay, just a minute. Okay, so here they're given the derating factor for the shock module installed in Berlin, which have an ambient temperature of 9.8 degrees Celsius. Okay, so you can take this directly as 9.8 and you can do the calculation. To get just a clarity, we are doing it again. From the ambient temperature and the cell temperature, you are calculating. Ambient temperature is 9.8 and the cell temperature as per the standard is 25 degrees Celsius. And we guys are getting it as 34.8 degree Celsius. But when you find the difference, definitely 9.8 is the extra temperature is existing in the system. You're going to get it as 34.8 degree minus 25 as 9.8, nothing special. So this value again you're going to multiply it with your temperature coefficient parameter, which is available in the chart, that is 0.85% converted to decimal. So done already. So when you multiply these two quantity, the difference of cell temperature and your temperature coefficient, we're going to get an answer called 0.04753. So we got an answer as 0.04. But when I want to find out the resultant temperature, that should be subtracted from 1 because it was a standardized condition. To calculate derating factor temperature, it must be subtracted from 1. So 1 minus 0.04753 is nothing but you're going to get an answer as 0.95247. 0.95247 means it says that you're achieving a resultant temperature efficiency of cell up to 95.25%. Actually, it is a good output, is it? The temperature efficiency is 95.25. So this is how your derating factor with respect to temperature will affect the power output. Hope you guys have taken this calculation part. Last class only you have taken, right?
Yes,
Okay, fine. So same thing has been given here. So based on that, based on the temperature variation or temperature significantly specifies where we are achieving a good output and medium output. So Sydney got 88.8% and Berlin got 95.25%. So you cannot say, yes, everywhere I'm getting the same output. Depending upon the place, depending upon the area, you're going to experience the different temperature outputs. Okay, so losses will also vary. Okay, so that's what they say. You have to check what exactly the temperature at that particular place. And you're going to check out how much of radiations we are receiving it, how much of radiations is not received for the cell. And when you compare these to cold region and a hot region, so we'll assume, okay, but see, normal climate itself, we say we are getting good output instead of cold areas, because as I said, the scenarios, the reaching irradiation to the cell is very, very less, first of all. So their conversion itself very less. Photons are converting from light energy to the electrical energy is less in cold area. That's what we cannot achieve the standardized output. But in this case, like normal climate or desert areas and all, we are getting high radiation. Of course, temperature losses are there, but conversion of energy is more as compared to your cold region. So that's what they're given. However, it's important to note that PV system in cold climate will not necessarily have a greater power output, because we say cold area, good output, temperature losses are less. So this assumption we have, but warmer climates are characterized by good solar radiation, while colder climate tend to experience shorter days and less sunshine, because throughout the year your irradiation period will be very, very small in colder area or colder place. So that's what I cannot say you go and generate electricity or implant your solar panels in colder area because of these losses, where you'll go to experience a very less days, a very less number of days where you get a sunshine. So this is one of the huger point which affect your output of a system. The next, dirt and soiling. And we already know dirt, what exactly this dirt and soiling. This is like day to day. See, we are cleaning our houses every day. I cannot say I cleaned today, I will not clean up to 1 month. I cannot say those words, because every day dust, it is not visible. But if you clean a swipe, you can see how much it is there. So similarly, we are implanting our PV modules outside. It is like outdoor application, not indoor. So outdoor means definitely dirt will be built on the surface. And due to that, because your cell efficiency of receiving the irradiation will go down technically, is it? And of course, outer look, it is going to create a layers. So layers means the capacity or receiving capacity of the collectors will reduce it. It acts as a shadow. It will act as a covering the surface. So due to that, your conversion of energy will definitely reduces. So here, that overall part of dust accumulation on the surface. So we'll separate the concept. Dust and dirt is one concept. Okay. So dust accumulation over the surface of a module, we call that as a soiling. And due to that, your output will not be reached as the expected. So it is creating a loss. You can call that as a soiling losses. I can read that. Losses caused by the buildup of dirt on the modules are often known as soiling losses, or often known as what? Soiling losses. So in the first module only we have discussed what are all the chances and what are all the things can be accumulated. So here they're given dirt, debris that can be placed or that can be going to cover the surface of a PV module. So leaves means definitely they will shade. Dirt means it will accumulate, which is not visible, but still that will going to reduce the output of a system. So here, this dirt and soiling is depend upon your orientation also, how you're placing your collector, because we know so many different types of mounting systems are available. In most of the pictures we have seen, they are in a slant position. If not, your roof will be in a tilted position or a slant position. So if that is the case, then we can say, okay, fine. Somewhat it is cleaning by its own, because the customer or a consumer, what we are using it, we are not going and cleaning or sweeping that collectors every day. We are not doing that job, is it? So it has to be done naturally. So that's what you can reduce that power losses by making a proper tilt angle or a proper orientation, because one of the natural gift that is a rain. So if it happens, so it will going to clean and wash it. If it is slant, definitely it will wash away the dust also, wash away that leaves also. But if you think if it is not slant, if it is completely horizontal, like a sleeping line, so what happens? If rain comes, whatever it is, again it will create more accumulation at one particular cell where the cell cannot operate at all. So that problem you will go to face it. That's what they say. The reduction in power output will depend largely on the site and the factor influencing soiling. Which are the factor? That is tilt angle at which the modules are installed. Okay. So as we say, if roof is tilted, okay, you can implement as per the design. If not, try to make it as a small tilted type of a mount. Okay. So the dust level on the site, and of course another factor where you are locating. Some areas, greeny areas, you can assume leaf will be going to shutter on the surface, or else let us assume you're there in the constructing area. So constructing area or near roadside. So because of vehicles movement on the dust will be accumulated much more than the area where you're out of the city, out of your urban areas. So that will also specify how much efficiency you are getting lost there. So dust level on site, local pollution that may form a film on the glass, and you have to think about the frequency of rainfall. So place wise or region wise, we have a different segment. See, if you say in Bangalore itself, we say, okay, near our college, we are getting a rain. But if you go near Hunsamanali also, you're not getting rain. Only small distance of 3-4 kilometers, we are finding so much of difference. Is it the same way? So that is all environmentally happening cases. So that also we have to consider how many months it is happening. Is it area is really we're getting rainy or desert area, so you cannot find it, is it? So those all parameters has to be considered for dirting and soiling condition. If not, of course, manually the maintenance has to be carried out. So in that case, so as we know, dirt derating factor, how it will be evaluated? There are two cases. One is, as we assume the place is having a less dust and frequent draining is happening, frequent draining area. So in that case, what happens? It will clean by itself. So your work or your maintenance will be reduced. So in that cases, and another one where you not have a frequent draining. So in that case, what is the calculation? So you can see here the derating factor due to soiling can be only estimated. It is a fairly common practice to use F dirt as 0.90. 0.90 normally they take it as first case, that is 10% output reduction due to soiling. Okay, for very dirt site, means this is like you're assuming it as a the place is having a frequent rainy and your tilt angle is proper, so that you can assume just 10% reduction in the output due to soiling system. But the area where you don't have a frequent rainy and all, in that cases, you are considering it as very dirt site. So this is for very dirt site 10%. But another one, sorry, F dirt, where you are assuming frequent raining and all. So this is just 5%. Means it is washing by itself and no need of much maintenance and all. So you can consider it as 5%. So 5% for the area where you have a frequent rain and 10% for area as lesser than that condition. So dirt and soiling will also affect your output of a system. So next is manufacturer tolerance. So I hope this is already used in the calculation part. Manufacturer tolerance, it will be given in terms of positive or negative. So this is based on the capability of your power output. If you consider one module, they'll say this is 315 watt will be given, 350 watt will be given. So in that case, plus or minus values will be added as a tolerance, as your resistance. See, when you see the color coding, we have one more term called tolerance. You're going to add it as a silver, you're going to add it as a gold based on a color. So here also same thing, that manufacturer tolerance accounts for the small output variation between individual modules. This varies with respect to the places or countries. Some company you can say that company will going to give this modules have +3, one particular company. Another company will say -5. I think these are the two standards they are using it, and this was given in this book. So -3%. So in that case, the peak power of the module may be 3% less than the given data sheet. -3. So if you assume your actual output voltage of the module is 315, in that case, what we have to do? We have to minus minimum 3%, because it is given 3% of tolerance has been added up. So that's what it is minus. You have to remove that, and your guys are going to get the output as 305.55 watt because of minus 3% of tolerance. Similarly, if you consider a positive tolerance, so plus 5%, please add the 315 plus 5%. So your output will be more than 315. That is like 350 something you're going to get it. So that's what every time you have to observe the data sheet, what exactly it is given. Is it a plus tolerance or a minus tolerance? So next is shading. So shading, of course, it is like almost the same as your dirt and soiling process. The effect, it is not accumulation, it is definitely the shading portion will be varied as the day moves off or the sun movement goes from morning to evening. If you have a building, neighbor building is higher than your houses, or you are staying near a hill station, or you have constructed a chimney, you have so many cable dishings and all. So in that cases, it is like purposefully the shadowing we are creating it, is it? So shading can be a major contribution to loss of the system performance for two main reasons. So before saying this, I will say shading, there are two category you can find it. One is partial shading, another one is fully shading. So partially shading is mainly with respect to voltage parameter, and fully shading is mainly with respect to your short circuit condition. Partially shading means what happens if you assume, let us think. So this is your module. So in that module, only one cell is get affected, and remaining portions are getting a proper radiations. Okay, so this is called partial shading. Here, this is only a port where you're not having a conversion and losses are happening because this cell is not contributing anything, not converting anything. But what happens due to this radiation area, huge heat will be concentrated on this particular cell, and it can damage the output of a module. The module in the sense your cell damage can happen and it persists for a longer time, then it will affect your module output. Similarly, if you consider complete shading, so complete shading means what? Your module output will be completely nil, is it? So but the thing, your shading will be taken part by part sometimes, or half of the area will be covered, so that we have to think it. So in these cases, normally when we implement for PV panels, bypass diode will be connected. Means you people are creating a minimum flow path for the current, so that you will have a continuity. Because let us assume you are having the three segments of module here, and you are all connected together, because we are making in a series combination, then connected to parallel, and afterwards you're drawing the power. In that, if mid one is not working and first and second are working, then this mid should not affect your first and second, third port, right? So in that cases, what they'll do, they will use two kind. One is bypass diode and one is blocking diode. So that will be used, and so that it will help for the module performance and safeguarding your modules. Okay, so this is exactly how shading will affect. So we'll see here what exactly. Hello. Somebody wants to speak? I don't know. Is it audible, right?
Yes, ma'am.
Okay, fine. No, somebody raised the voice, that's what. Okay. Shading leads to a voltage drop, and if enough of the PV array is shaded, the voltage may drop outside the inverter voltage window, causing the inverter to turn off and the system will produce no power. So here, this shading we mainly concerned about the conversion energy. Already your inverter will be selected based on the PV capacity. So, and the limitation is already given. So in the last problem, we know that the range has been given between 264 to 600. 264, minimum 264 must be reached your input of inverter, then only it will take off for the conversion process. But if it falls below that, then your inverter will not turn on to make the conversion of your energy. So in that case, if you're shading, I don't know how much far it is going to shade. It's a full cell or a half cell or a quarter cell. So depending upon that, there is a drop in voltage. And this drop that can cause the output, what we are drawing from the PV panel can be less than the requirement of your inverter input. So that is one case where your inverter will not turn on and gives the power output. So what we say that the system will produce no power. Means no power means no conversion, nothing you're going to get it. Another one where multiple strings are connected in parallel. The shading on one string may impact on the other orders. So this is because current and voltage are directly affected by the irradiance received. And when the module is shaded, it does not receive as much irradiation. So let us assume this as number of strings, because when you go for a huge range and all, it will not be one or two. You'll have a multiple strings. Definitely, back to back, it will be connected and you're drawing the power. If one cell is affected, your definitely efficiency will goes down. And shaded area, it will not receive much radiation, much conversion. And I also already told you the silicon, it will need minimum 1.1 electrovolt conversion at a time. If it is less than that, then the photons cannot be used. The shaded area normally it faces the problem like conversion of energy because of low value. It will not take place. So that will going to affect your output in terms of current and in terms of voltage. Voltage drop will also happen and movement of current will not take place, and that create a less power or no power in the output of a system. Okay, so this is with respect to shading. I think I have one of the data sheet where it shows the tolerance and how the value has been given with minimum and maximum. You can see it here. So this electrical data sheet has been given based on standard conditions, that is 1000, that is the irradiance, minimum irradiance 1 kilowatt per meter square, and your air mass is 1.5. The temperature expected is 25 degrees Celsius. See, they have given the derating factor, particularly with respect to mechanical tolerance, that is +5 -3. So, but standard value is how much? 350. Which one you are using? Based on that, you add +5% or -3%. And next they're given rated voltage, it is 54.7, current has been given 5.76, and next major parameters for calculation: open circuit voltage, short circuit current, that is 64.6 and 6.14, and system voltage has been given 600. And you can see the temperature coefficients with respect to different conditions like power, voltage, current has been given here. And finally fuse rating. So series fuse rating, this is very important to see from electrical data so that you can find out, is it necessary to have a production system or not. If it is below this value, you say no need of production devices. But if it is more than this, definitely we have to go for a fault protection in terms of overcurrent relay, overcurrent protection, lightning, grounding, all these things have to be considered. Fine. This is one of the important topic where they can ask you in exam, and please elaborate it. Don't minimize your answers because it will be asked for 8 to 10 marks. Try to give major importance with respect to the points and highlight it. Okay. Any doubts regarding this?
No, ma'am.
Only one answer I'm getting, only Soundarya. What about others?
No, ma'am.
Only no is the answer. How many people are experiencing this? Because how many of you are using this application of solar PV cells in your houses? Most of you? Sai Ramesh, Shashikant, Bharat. Are you?
No, ma'am.
Can you hear my voice? Is it audible?
Yes, ma'am. Audible.
Okay. Yes, I'm asking, are you experiencing this? Means you cannot know actual term, but you can see the output of a system, shading, dirting. Day-to-day life, there is a variation of temperature, is it right? If anybody is using a solar panels for your particularly water heating purpose, we can say summer, there is no need of using any other extra like geyser application for boiling water. But in winter, in rainy season, we want alternative because we cannot expect that, okay, the water will be heated because there is no sun means we assume, okay, the temperature or boiling capacity of the water will not be reached up to the mark and it will be just like more than a normal Celsius. So in that cases, you can apply this concept. Of course, there is a irradiation level or a rays reaching the collector are very, very less. Okay, so remember these points. And this is one of the important question. If you have any doubt, you can ask me. Okay, fine. Shall we wind up?